Hello guys, today I am here about to explain signal approximation using orthogonal function and mean square error. The contents in this section is signal approximation using orthogonal functions and mean square error. First, what is signal approximation using orthogonal functions? Consider n real signals x1 of t, x2 of t, x3 of t, and so on xn of t as a set of mutual orthogonal signals in the n-dimensional signal space over an interval t1 less than or equals to t less than or equals to t2. The condition for orthogonality is integral t1 to t2 e power m t xn of t dt equals to where 0 m equal not equals to n en m equals to n where en equals to integral t1 to t2 xn of t whole square dt. It represents the energy of the signal for all n signals. Next, now any function f of t can be approximated in terms of mutually orthogonal signals x1 of t, x2 of t, x3 of t, and so on xn of t, called the basic functions over the interval t1 of t, t1 less than or equals to t less than or equals to t2. ft of t is equals to c1 into x1 of t plus c2 x2 of t plus c3 x3 of 3 and so on up to cn xn of t equals to summation of n equals to 1 to n cn into xn of t, where c1, c2, c3 and so on cn are the constants. If the error signals is fe of e, then the f of t equals to summation n equals to 1 to n cn into xn of t plus fe into t, or f of et equals to f of t minus summation of n equals to 1 to n cn into xn of t. For the best approximation, the error signal should be minimized, that is minimize e equals to 1 by t2 in t2 minus t1 integral of t1 to t2 fe square of t dt, that equals to 1 by t minus t2 integral of t1 to t2 mod of f of t minus summation of n minus 1 to n cn xn of t whole square dt, where t1 less than or equals to t less than or equals to t2, where E is called a mean square error for power of the error signal. Next, we know that the necessary conditions to minimize the mean square error is respect to the constant e is equals to 0, j 0, j equals to 1, 1, 2, 3 and so on up to n. So that implies these equations are further given in this. While expanding the integration terms, notice that orthogonality, the cross product of the orthogonal functions are 0. This means that all the terms other than the jth term without cj are 0. Hence, these are the equations. This equation is equals to 0. So, the remaining two non-zero terms are these two terms are equals to 0. Changing the order of differentiation and integration, integral of t1 to t2 minus 2. This is the equation differentiate and equals to 0. Next, this integral of t2, integral of t1 to t2, 2 into f of t xj of t dt equals to integral of t1 to t2, 2 into cj xj square of t dt, or Cj equals to integral t1 to t2 f of t xj of t dt by t1 to t2 x2 of j t dt. Here it gives equals to uh, integral t1 to t2 f of t xj of t dt by ej. Thus, for the best approximation of the function given in the basic constants should be chosen from final equation. Next, what we know, well, first we discuss about the mean square error. The mean square error can be indicated as MSE. The signal approximation can be evaluated from the orthogonal functions when the optimum values of C1, C2, C3 and so on Cn are obtained from the equation of the signal approximation using orthogonal functions. Cj equals to 1 by Ej integral of t to t1 to t2 f of t into xj of t dt. Now the mean square error is E equals to 1 by t2 minus t1 integral of t1 to t2 mod of f of t minus summation of n equals to 1 to capital N Cn into xn t mod square dt. Here E equals to 1 by t2 minus t1 into integral of t1 to t2 f square of t dt plus summation of n equals to 1 to n c square n integration of t1 to t2 xn square of t dt minus 2 summation of n equals to 1 and cn integral t1 to t2 f of t xn of t dt. From this equation, the signal approximation using orthogonal functions. Therefore, the MSE is, that means the mean square error is E equals to 1 by t2 minus t1 into integral of t1 to t2 f square of t dt plus summation of n equals to 1 to capital N c square n e n minus 2 into summation of n equals to 1 to n cn into cn en, that equals to 1 by t2 minus t1 into integral of t1 to t2 f of t dt f square of t dt minus summation of n equals to 1 to n c square n e of n, that equals to 1 by t2 minus t1 integral of t1 to t2 f2 of t dt minus c square 1 into e1 plus c square 2 into e2 plus c square 3 into e3 plus and so on plus c square n e of n. Thank you.